As we discussed previously, we need enzymes to facilitate the breakdown of starches and other disaccharide sugars, right? We need to convert into monomer units before we can make energy out of the carbohydrate. And molecules that achieve this are in the class of enzymes. These are proteins. We'll talk about proteins in the next module. We'll often show these larger molecules by the following kind of ribbon and coil structures that can give kind of a feeling about what the structure looks like. Although it kind of looks like a mess here, definitely you're not intended to get anything out of this structure. We'll talk a lot more about proteins coming up. The different colors can often mean different strands that are coming together to make a larger protein. But in any case, this is salivary amylase, and it is the enzyme that works on amylose and amylopectin, right? The name amylase reacts with amylose. It's what breaks down that particular carbohydrate. And so how do these work, right? Well, remember that idea structure determines function. I think this is a perfect example of what that is. Well, the enzyme here is in gray, and we have the substrate, which is what the enzyme is going to act on. So in this case, if we're considering the enzyme amylase, salivary amylase in our saliva, salivary amylase is going to act on amylose, amylopectin. And that's the substrate. That's what's going to be acted on. The enzyme has an active site that captures that substrate temporarily. And as this binding happens, the enzyme is going to kind of grab onto it and lock it in there. And as it locks it in there, it makes it easier for whatever reaction it's associated with to occur. So in the case of salivary amylase, it wants to break off the products. And it's going to do that, right? It's going to shift the shape so that it makes the products break apart and then release them. And so the enzyme, in effect, facilitates this reaction. That hydrolysis, glycolysis, doesn't really occur on its own nearly as easily as if you have something that's kind of pushing everything into the direction it needs to go. Enzymes do that, and because they're so dependent on the shape and the structure of things, they need to shape that molecule in a specific way to that specific molecule's reaction. When we have starch or glycogen, right, larger molecules, we begin with salivary amylase, and that can break things down into disaccharides, and the disaccharides, they have their own enzymes that are going to work on them. So maltose, that's two glucose linked together, is broken down by the enzyme maltase. Sucrose, that's a glucose and a fructose, that's broken down by sucrase. Lactose, lactase, and we talked about how lactose needs its own special enzyme earlier because of that beta-glycosidic linkage. And so, when we look at enzymes, they replace, their naming rather, replaces the name of the object they function on with ase. So maltose is broken down by maltase. Sucrose is broken down by sucrase. And so when we're looking at enzymes, their name really refers to the object upon which they act. That really is key to their definition. We can look at the following example. This is sucralose, which is Splenda, and maybe this is something you've heard of. This is artificial sweetener, and so it tastes sweet. If we look at these two examples, and note that the glycosidic linkage that's kind of bent for sucralose, that's just stylistic. It's the same thing. Sucralose tastes sweet, right? It's got that very similar structure to sucrose, and our taste buds in our tongues, they're not really, the exact same thing as the metabolism, so they experience that taste, right? But if we look at sucralose, it has 3 chlorine molecules on it, and these chlorines are large, right? These chlorines are, they're bulky and they're different, right? They make the sucralose molecule different from sucrose. And because it's different from sucrose, sucrase is not able to connect with sucralose. And so it cannot be broken down. And because it can't be broken down, it can't be metabolized. And if it can't be metabolized, you can't get any energy from it. And therefore, it doesn't contain any calories. And that's the point of why sucralose is appealing, because it's calorie-free, but still sweet. The reason why it's calorie-free is because the enzyme sucrase is not able to capture the sucralose and break it down in the same way it's able to break down the sucrose. Now, as far as the health effects of artificial sugars, that's a little bit outside the scope of this course, but as far as the basic biochemical mechanism of why it works, this is why it's not able to be broken down, yet it still tastes sweet. Okay, this is also a little bit outside of the course, but I think it's a really important thing to add on because we break down glucose, and then what, right? We get glucose, and what happens next? Do we just use a glucose to get energy? Well, not exactly, right? Biochemical processes derive energy from a molecule called ATP, which we're not really going to have be a huge part of this course, but I think is worth mentioning to bring the whole thing full circle. Once we get a glucose monomer unit, there is a very multifaceted set of reactions that occurs to creating ATP by breaking down glucose all the way. And so ATP is really easy to use energy. This is that energy that couples to other reactions and gives us the oomph that's needed to make non-spontaneous biochemical reactions occur. And key to this is in these quote-unquote high-energy phosphide bonds. So ATP is adenosine triphosphate. The charged-up version of ATP has 3 phosphates there. And to deplete a little bit of energy out of it, we lose one of those phosphates and we create ADP, so diphosphate, right? There's 1 phosphate in the bottom all alone, and the ADP molecule has 2 phosphates left over. This gives up energy. I would think of this, ATP is the charged up version, ADP is the decharged version, and ATP is the molecule that gives energy to reactions that need it. When we consume glucose, that generates energy, and we can recharge the amount of ATP by converting ADP and lone phosphates into it. 1 glucose will recharge 32 ATP, and that breakdown is what leads to this molecule that is directly responsible for the energetics of our processes.